Welcome to Real Learning Center. We're going to basically look at today, starting with a new topic called atomic physics. So we are basically covering how do the atoms behave, how do the electrons behave, and those kind of things inside the atom. We go inside the atom in atomic physics, and we also will touch upon radioactivity, where we need to even go inside the nucleus. And the second and third videos are more into the nucleus, whereas the first video is more into just the atom level itself. So we'll start with the atomic physics, where we talk about atomic models. So what is an atom? So it is not that people knew what the atom was from long back. So long back in the early models, what we say, atom was not even considered as one of the Dalton's atomic theory. It talks about basically atom being just an indivisible thing. Like you cannot even split the atom and see what is there inside. So atom was supposed to be basically something that is the minimal, most smallest part of anything, and it could not be divided. Whereas in early 20th century, when J.J. Thomson first basically discovered these electrons, he came with this idea. There are small particles called electrons are there in the atom, and he said that these electrons are negatively charged, and you can actually make electrons move in a particular direction by applying electric field into it and all that. So when he found out about these electrons, then he started theorizing about what is an atom. What is it atom? Because we know that atoms are electrically neutral. In the sense, any atom will not have any effective charge. But electrons which are there in an atom are actually electrically charged, and they are negatively charged. So how is an electron neutral when you have negatively charged particles inside it? So he came with a theory that inside there are also positively charged atoms. Positive particles are there, positive charge is there inside the atom. So he came with this theory that uh, the whole of the atom looks like this. What he calls it as a pudding. Okay, it's a pudding, like a cake pudding, where its the whole thing is positively charged. You can see that whole thing basically is white part is positively charged, and in between you can see those small dots, rounds, which are basically electrons which are negatively charged. So that is his theory. So his theory was basically about plum pudding model, where it is about full of positive charges everywhere, and in between here and there are electrons which are basically negatively charged. But the positive charge of the whole area amounts to be equal to the exact amount of negatively charged electrons that are there, the total amount of charge. And hence he says the atoms are actually neutral. Then there is some difficulty with this notation and this notion, and Rutherford actually just came afterwards, and he did one experiment to see whether this is true. So he wanted to see whether the plum pudding model is true or not, or is there any other model. He wanted to see inside the atom. So he chose actually certain particles to go through a very thin layer of a material. So he chose gold as a golden foil, a very thin golden foil. So he chose. So and he made some particles called as alpha particles go through it. So he actually created an experiment where this gold has this nature that it is highly malleable, in the sense that the gold actually can be beaten down into very thin sheets, very thin. How thin? Like 8 to 10 atoms thick, so thin. Okay, so it is possible to do that with gold, but not with other elements. So that's why he chose gold. And then he also chose alpha particles. What are these alpha particles? He found these particles. They did not know what alpha particles contain. At that time, actually, they saw that they have seen something called as radioactivity. From there, they have seen some particles are emerging. So, but they are able to characterize these particles. They said that these alpha particles are actually having some mass and some charge and all that. So he thought he can use that as a bullet to go through that the it is charged. So when you go through it, his idea was this: if you shoot an ray of alpha particles into the gold foil, since gold foil is fully positively charged, like plum pudding completely arranged, and when you shoot it, the alpha particles are also positively charged. They are repelling, so they will come back. There is no space to go also. They'll have to come back. That is what his theory was. So he wanted to see whether that happens. So what he did was he put all around photographic plate, in the sense that photographic plate is something that where light falls on it or any particle, charged particle falls on it, it will actually get exposed and you can see that that area has something fallen on it. So he saw that when he observed the photographic plate, most of the alpha rays that he sent actually went through its right and hit it at the other end. Whereas a few of them actually, yes, diverted, and very few of them actually came back. And it kind of puzzled. So let's understand a little bit deeper into this experiment. So you take this scenario where there is this gold foil. Okay, I have written a slightly thicker one, but in reality it is actually a 8 to 10 atoms thin, a very thin gold foil. I mean, very, very thin, in 1,000th of a millimeter kind of thing. Okay. Uh, so now he actually sends these so-called alpha particles uh, using certain equipment to go through this. And when he did that, you see that actually most of the alpha particles actually entered inside. And you saw that one or two went away, slightly deflected, and one came back. So what is happening? How is it going through this? So what is this gold foil all about? So if you see, I want to take one small piece of the gold. Okay, that is the thickness of the gold, and I want to zoom it up and see what is there in that. The theory was that it contains actually lots of gold atoms. So these are all gold atoms, very nicely packed. You can see how they are packed, gold atoms. There is no space anywhere, and each atom is actually like a plum pudding with full positive charge, and here and there one negative charge on that. But this, what is this alpha particle? If you zoom up the alpha particle, you will actually see it is nothing but actually there is inside. If you see an alpha particle, it has a charge too, two charges. If electron is one charge, this is double the charge, and the electron is negative, but this is positive. So during those days, people were knowing that charges can be positive, negative, and how much charge are that. Okay, this is double the charge of an electron, and it is almost 4 times the weight of an hydrogen atom. So that also they knew. Okay, they were able to measure that. So they had that in picture. So now that is an alpha particle, and such an alpha particle actually enters this gold foil, which is basically naked, packed with these atoms, and all of them are going through, and very few of them are coming back, hitting that. So that means that whole of our idea that it is actually packed like this positive charge seems wrong, and J.J. Thomson's plum pudding model seems wrong. So Rutherford actually did this experiment and he came out with his own model that we call the Rutherford atomic model. So what did he do? He said that no, it is not packed like this. Instead, actually, it is nothing but one small dot, a completely concentrated areas, very small area, okay, of basically positive charge. And around that basically is all empty space, completely empty space, except that here and there some electrons are moving around. So, in such a scenario, actually, you see that whatever you thought was completely filled with positive charge is actually not true. Positive charge is concentrated at the center in a very small, dense area, and the remaining part is all empty with some electrons with negative charge going around. So, if you assume such a model, okay, then you can explain why we can say that uh, most of these alpha particles actually went through. So you now put back the same model here instead of earlier model. Now this is, you can see that each one of them actually is a atom which is basically having in the middle small positive charge, and around that is all empty space. So it is like basically, now I have written even an exaggerated picture. Okay, in reality, you assume that there is a huge room here. Okay, that is an atom. Assume that huge room is an atom. Then the size of a small ping pong ball is basically probably a nucleus. So you keep in this whole room, one big hall room, you put one small middle, one ping pong ball. Okay, and then there are electrons. A few electrons going around. So you can actually equate that to like a few mosquitoes going around here. Yeah, just some mosquitoes going around in this area. Now we are going to basically get alpha particles ramming in through this hall. So what are the size of the alpha particles? Maybe in this scenario, a peanut. Yeah, it is like few peanuts coming in here. Now, what is the chance of those peanuts, alpha particles, hitting that one single uh, ping pong ball size nucleus? Very less. So whatever hits there will go back, but all the remaining will actually go through it. So like this, you can see that all of them just went through, and one-half cases basically reflected back. So as for Rutherford, basically, that atom now actually is not anymore like a positively charged distributed. Now it is a positively charged at the center in the middle, and the electrons actually, he thought, how are these electrons? They are moving. Okay, they are moving like this because they are there everywhere, and he can only attribute it to the moving like see during those days. The observation of the planet going around the sun was actually known. So they wanted to model it like that. So Rutherford said that it is actually moving around, uh, the electron is moving around the nucleus. He called the middle one as nucleus, like this. So that is his model. And he did this in 1911. His model came out in 1911. So he discussed, saying that, there is, if you now send basically the alpha particles to that, there is enough space to go. So he can easily explain why alpha scattering experiment worked that way it worked. However, in his theory also there were some limitations, some questions unanswered. What were the questions unanswered? The most important one being, what will happen to the multiple electrons? If there is one electron, fine. If there are more electrons, do they go on the same circle, or do they go on circles of different radius? He had not mentioned that very well. It was an unanswered question. And then second question was, are all of them like planets on the same plane? Are one electron going like this, other electron going like this? So in different planes, is that possible? So no explanation on that. Okay. Plus, it was also a question, a very interesting question, more technical question was this. He says that do they actually, when going around, emit any kind of a radiation? Because an accelerating charge is supposed to emit certain radiation. Do they emit radiation when they are moving in a circle? That is another question that was there. So let us see how to answer these questions. So was there anybody who tried? What is the background for answering these questions? So there are two discoveries that had happened a little before that, in a few years, in a few decades before that. That was by two very eminent scientists, and from very different backgrounds. One of them is actually James Maxwell. The other one was Jacob Balmer. Okay, both were almost living in the same simultaneously together, different places, of course. The Maxwell was actually a student of Michael Faraday. Michael Faraday, you must have known. You must know that he's actually done electromagnetic induction and all that. Dynamo generator. He was a very practical guy. James Maxwell was actually a mathematician, a very theoretical guy. So he came with this concept of electromagnetic waves being nothing but the electricity and magnetism are not very different from each other. They are linked in the form of electromagnetic waves. So he came with a theory of electromagnetic waves, and he became very famous for that. And that theory, let's understand a little bit and see how that will impact our Rutherford model of an atom. And Jacob Balmer, on the other hand, was also very good at mathematics, but he also did conduct a lot of experiments. He was actually a PhD, but he went back to teaching school. He was a school teacher, yeah, conducting lots of experiments also. He came with a very interesting experiment on something called as hydrogen spectrum. So he came up with he devised a method to basically capture a spectrum of hydrogen. What does it mean? We'll see that. And how is that going to impact Rutherford model? So we'll see both of these. So let's start with basically Maxwell's ideas. Before looking at Maxwell's ideas, so we have to refresh a little bit. So you see here, if electrons are actually moving in a conductor, okay, if electron is stand still, you know that it produces electric field around it. So electrons are moving in a conductor, which means basically it is current is flowing. So when current is flowing, there is a magnetic field that comes around that. So who said this? This idea was not from Maxwell. This idea was from Oersted. Oersted basically saw that when you make current flow through a conductor, you can see magnetic field around it. So moving electrons create magnetic field. That is what he saw. And then later came Michael Faraday. He did a little different. What he did was he actually took a magnet and put that into the into a coil. And when he was inserting and removing inside the coil, he saw that some current gets produced in the coil. So then he came out with this idea that in Faraday's idea is that moving magnetic field actually creates electric current. See these two things, no, they are very complementary. Moving electrons create magnetic field, and moving magnetic field creates electric current. Electric current means moving electrons. So moving electrons create magnetic field. Moving magnetic field creates moving electrons. Interesting. So he actually came with this idea. And then when you say moving magnetic field, he also showed that it need not be moving magnetic field, it is just a changing magnetic field. Here he used a bar magnet to move it. But you could always put a wire around that and change the current through that and change the magnet. So it need not be just movement, physical movement. It is the changing in the magnetic field that is important. So now Maxwell actually combined both these ideas. He says that you take an accelerating charge, an electron. Okay, accelerating electron, what will happen? Let's think about it. Accelerating electron. First of all, it is moving. Because it is moving, it creates magnetic field. Since it is accelerating, that means the movement is changing. The magnetic field also is changing. That means an accelerating electron creates a changing magnetic field. Interesting. Now that changing magnetic field, according to Faraday, has to create some current. That is, it creates this electric current. So that electric current means electric field it generates. Not just current, it generates current will happen if you connect it, but otherwise it creates electric field. And that changing electric field in turn creates actually magnetic field, which is again changing. If you make sure that you have an electron which is continuously accelerating and the change in the acceleration also is changing and change in the change also is changing, like that if you create something which will happen actually when you do a circular one. Okay. So if you create a circular path for anything, this can happen. So he says that circular path, if you put an electron to that, then it creates changing electric and magnetic fields, which we call actually as electromagnetic field or electromagnetic wave. So an accelerating electron produces an electromagnetic wave according to Maxwell idea. Now, that actually means that in our case, if you say to the applying Rutherford model, Rutherford model says that an electron is moving around like this continuously. That means it is accelerating because the speed may be same, we don't know, okay, may be same, but its direction is changing. If the direction is changing, that means it is accelerating. The change in velocity is acceleration. So it's moving, it's accelerating. So accelerating electron has to produce electromagnetic waves. So we can say that it is producing electromagnetic waves like this. So, do they produce electromagnetic waves when electrons are going around in a circle inside the atom? Do they really produce electromagnetic waves? That was the question. So now the question is, so at least the theory says so. So now somebody has to practically see. So let's say how to see this. So to see whether it produces electromagnetic field or waves or not, there's a technique. So you see, you can actually split the light into constituent colors that you know. Okay, you can actually send the light through a prism. It splits into constituent colors. It's what we call dispersion. Now there is an instrument we call actually as a spectrometer. Okay, you see this instrument spectrometer. What you see here is in the middle there is a small turntable on which we keep the same prism, okay, in a flatter mode, and make sure that we actually send some light through this. Okay, we send a light through this. You can see that light goes through this. It focuses the light properly. It's a well collimated light, nice light with a line like this goes through that, and that splits it into multiple colors and comes out to the other one. It is again properly focused, and you can actually watch it through that other side. So when you watch it through the other side, you see very clearly the lines, what we call as spectrum, color spreading across like this. That's what you watch inside. And this is what white light contains. So it is also now split into its own colors. So this spectrum is called as a continuous spectrum of white light. So now this particular instrument which does that is a spectrometer. The spectrometer is very useful in calculating or in seeing various colors of light and also properly measuring them, what their wavelengths are and all that. So now if we take it a little further, okay, instead of actually putting sunlight, we will put a sodium vapor lamp. So if you put a sodium lamp and the light goes through that in the same way and you see it, you actually see just two lines of sodium, just two lines. Okay, these sodium lines are yellow lines. They're called sodium yellow lines. There are two lines. Yeah, and if you actually very accurately measure the wavelengths of those lines, one of them is 539 nanometers, other one is almost 540, like 539.6 nanometers. Just two lines. So that signifies that it is sodium. Sodium has exactly that much, those two lines. On the other hand, if you pass it through neon, for example, argon, hydrogen, helium, many of those lights means you can actually burn it. Okay, all of them, when you burn it here and see what is the spectrum it produces, what is the light containing. So you can actually tabulate it like this. See here, hydrogen actually is the top one, which gives so many different lines, and these are all called line spectrum. There is not a continuous spectrum. Wherever the lines are there, only there you are getting. Other places is all dark. So you can see helium is there and neon is there. So you can see sodium has two lines. So all of them are actually, each one you can see it and get different lines. So this was first actually observed by Balmer. Okay, he was the school teacher. Okay, Jacob Balmer is his name. So he used to work with the spectrometer and trying to see using hydrogen. He created an emission spectrum of hydrogen. Okay, and hydrogen he saw when he watched that, he saw that there is only red line at about 656 nanometer wavelength, and then he saw one more line at around 490 nanometers, which is basically a kind of a blue-green line, and then more of a violet line after that. And there are many lines, very small lines on this, on the left side. When you come more and more towards the left, you can actually see that these lines are getting nearer and nearer, and they are also getting more and more lines, and they are also becoming slightly dimmer and dimmer. Yeah, this is how he saw. And he basically published a way of calculating these lines. I mean, he found out a formula for these lines, and I'm not going to put forward that formula. The formula is a very Balmer series formula, very interesting formula. Given the values of some n 1, 2, 3, 4, you can predict these where these nanometers are, the wavelengths. Okay, so he came up with this formula without knowing anything about how these lines are actually coming. He's fitting a formula. So now the thing is that when you go back to the our Rutherford model, so let's just try to see whether we can answer some of these questions using this knowledge. Okay, multiple electrons, do they move on a single circle? We don't know. Okay, the question that now comes is that we already know from electromagnetic waves of Maxwell that if it is going in a circle, it will produce basically electromagnetic waves, and this frequency with which it is moving, it is the same frequency, the same one light will produce. Now, if you are seeing so many lights, it means there may be so many circles. That is one way of interpreting. In every circle, basically, it is giving out some kind of electromagnetic wave. Yeah, but whether it is true, we will have to see. And then we also see that do they move in one plane or not, that we cannot figure out from this. Yeah, but however, the most important question is, do they emit while moving in circle? So it looks like it emits because we are able to see it. Whether it is emitting because it is moving in a circle or not, that we don't know. We know that whenever if something moves in that kind of a changed velocity, accelerated path, it has to actually emit. And we are seeing that it is emitting various colors. So maybe that is true. However, there was one serious problem. The problem is this. So you see, you have an electron and you have a nucleus. And the electron, let us say, is going around in a circle and emitting that red light. Yeah. So now when it is doing that, it is actually losing energy. So when it is losing energy, how long it can lose energy? When it loses energy, it becomes lower energy and it has to go nearby. Yes, and it becomes smaller circle. Then after some time it becomes even smaller circle. It should keep on losing energy, isn't it? So look at this. What really should happen according to the Rutherford model is this. It will actually start moving in a spiral and then go inside and get stuck to the nucleus. If this happens, if it is emitting the radiation, because it is emitting the radiations, it is actually losing the energy, and if it is losing the energy means it is becoming more and more nearer to the nucleus and finally gets into the nucleus. So, and now again another thing happens. If it is actually losing energy and its diameter is, its radius is reducing, that means that it has to, when smaller radius has to give rise to basically smaller wavelength, smaller frequency radiation. Okay, so it should give us basically continuous spectrum in all frequencies or all wavelengths. We should get light, but we are getting light only in discrete. There is no light in the middle of that. So all frequencies are not there. Some frequencies, I use frequency and wavelength interchangeably just to say that it's different light, different color light. So they are all there. They are not there. Only one discrete ones are there. So what is the deal here? So the question basically is, if Rutherford was right, electrons would actually spiral into nucleus, emitting a continuous spectrum. And we are not seeing continuous spectrum, and we are not seeing that it is spiraling into the nucleus and stopping the radiation. We are seeing that it is continuously radiating. That means that there is some problem. So what is the problem? What is the problem in Rutherford imagination? So let us see what it is. So next came another very famous scientist called as Niels Bohr. He came in the 20th century and he worked a lot. He is the father of quantum mechanics. He actually started quantum theory. So he came with this idea that it is actually electrons are actually going around not in one circle but many different circles. Different electrons occupy at different times different circles, and each one of these circles actually have associated energy. So there cannot be an electron in between these circles. So each one of these are actually called as stable orbits, and he named those orbits as shells. Okay, he says K shell is the nearest. Next one is L, M, N, O, P, like that. He names those shells. So we now give that as quantum numbers as 1, 2, 3, 4, 5, 6. Okay. So he named those cells. And what is important is he came up with very nice 3 postulates. Okay, his Bohr's postulate, which tells about what the his view of the model is. He says that an electron in an atom would revolve in a certain stable orbit without the emission of any radiant energy. That means when it is going around in the stable orbit, it doesn't emit any radiation. Interesting. He made that statement. So he made that statement, and he actually said that if it is going in the orbit, it doesn't actually have any, it doesn't lose energy. Hence, there is no question of spiraling back into the nucleus, and hence no question of actually losing energy. So he says that there is no energy. So, however, he says that these orbits are those for which the angular momentum is an integral multiple. See, he even came with the mathematics of how to calculate these orbits. If you take h is a Planck's constant divided by 2 pi, if it is the integral multiple of this, the angular momentum, when it goes around, there is an angular momentum. So if the angular momentum is basically integral multiple, only in those cases it can have a stable orbit. In other cases, there is no orbit in the middle. In the middle of these point, basically circles, somewhere in the middle, there are no orbits. Because in that area, if you calculate angular momentum, that won't be integral multiple of h by 2 pi. So he says it is only when there is h by 2 pi, integral multiple of that, then you will have a stable orbit. But now where is the light coming from? In the Balmer series, you saw that there is spectrum giving light. How is it giving? He says whenever an electron actually uh, goes from one stable orbit to the other stable orbit, either from lower to higher or higher to lower, whenever that happens, okay, then there is a radiation possibility. In the sense that when it is going from lower orbit to the higher orbit, it actually absorbs the radiation. Okay. And when it is going from higher orbit to lower orbit, it gives out the radiation. So the radiation, he called it as photon. He even gave the photon's frequency by using its energy, h nu. H nu is actually nothing but Planck's constant into its frequency. That gives the energy. So he said that if you take one of the orbits, let us say orbit number 2 to orbit number 3, so it is jumping from 3 to 2, assume. If it is jumping from 3 to 2, then it means that it actually is giving out a photon, okay, of basically energy equal to orbiting energy of 3 minus orbiting energy of 2. That is his third postulate. So it explains the Balmer series very well. See, look at this. Whenever it jumps from higher orbit to lower orbit, it is giving a photon. Otherwise, it is from lower to higher, it absorbs photons. So you can see this picture. In fact, what he said was basically it's not only true for one orbit. So if it is jumping from 1 to 2, you can see that red line. Okay. 2 to 1, you can see the red line. But it is going from 1 to 3, 1 to 4. So that time you see different lines. So he talked about basically how, depending on from which orbit to which orbit it jumps, it either absorbs or releases a photon of a different frequency or what we call different color. Hence you will see different colors in the Balmer series. It is continuously happening. This is called excitation of an atom. So he says that when the hydrogen is burning, atom gets excited, and therefore it gives you these colors. Interesting. So he says that each line actually represents the energy difference between the two orbitals. Every line actually represents that. And then he also said that still after all this actually explained very well in the sense of whatever the Rutherford's problems were there, he came out with solved most of the problems. Yeah, he even postulated that when it is going in an orbital, there is absolutely no energy lost. But that question is still unanswered. One question that is still unanswered is, how can you say that electron actually going around in getting accelerated, Maxwell says that something getting accelerated has to give off electromagnetic waves and lose energy. Why is it not losing? That is the one question that is still unanswered from the Bohr theory to start. Later he worked and improved his theory with many other people. So one of the improvements that came is from Broglie. So he gave an explanation of his second postulate, which said that in the stable orbits it doesn't emit any radiations. So he says that this de Broglie came with this idea, saying that electron can be also seen as not just a particle but a wave. And he said that electron, when it is in its orbit, it is like a standing wave. In a stable orbit, it behaves like a standing wave is something which is not moving. Okay. Electromagnetic wave moves away, means it loses energy. It's just a standing wave around that. And hence there is no energy dissipated. Energy is there in that place itself. So he came with this idea. And he also said that, see, because you can only fill in an integer number of waves in that, the circumference has to be some integer multiple of this length of the wave. Hence, you cannot have all the orbits. He said that is why you can't have all the orbits. You can only have some orbits of some certain radius. So, which is fitting well with the stable orbit concept of Niels Bohr. So, this is basically de Broglie's explanation of the second postulate. Now, however, even Bohr's theory has had some limitations. One of the limitations is that it was very difficult to apply this theory to atoms for more than one electron. Because if you have multiple electrons, helium will go next, more electrons are, even you further and further, more and more electrons are there. And now electrons are not only basically having the force with respect to nucleus, but it is having a force between themselves. And how do you model that? That became a big problem. Okay, that is the limitation of one of the Bohr's theory. He could not actually do more than he could not do a lot of calculations for more than this hydrogen atom. Then came one more important problem, was that his model is unable to explain actually the intensity differences. You can see that the Balmer series shows some intensity differences between those lines, and it was unable to explain those intensity differences. They are brighter on the right side and dimmer on the left side. Why so? Why certain transitions are preferred than other transitions of the orbits? That was not something explained by Bohr. So that was a limitation. So there are many more models that came later, and Schrodinger's atomic model, for example, after quantum theory came about, is just about is saying that electrons, I think we have to understand a little better. They are quantum physical objects. They are not like classical objects that are really hard like this, move around. They are like partly wave and partly particle type of objects, and there you can actually not predict exactly where they are at any point in time. So you cannot predict one line of circle like this. So like that, he talked about how do you measure this, and he said that it is actually kind of an electron cloud around a nucleus. The cloud in the simply says not many electrons, it is one electron. Even if it is one electron, you can find that electron anywhere. You just look at where the electron is, it may be found in anywhere. Now, in that area, if you find out how often you find it in a certain range in area, defines the probability of that. So, if you see where there is a little bit thicker area in that area is called actually an orbit. Okay, the orbit is not such strictly defined, it is slightly vaguely defined according to Schrodinger's atomic model. So, the current theory actually comes out with many other kind of ideas on atomic models. They also got into the nucleus and trying to understand what happens within the nucleus. So now, with this actually, we are going to conclude our basic understanding of atomic models, of important atomic models, and we will move on to nucleus and then move on to the radioactivity and how that happens in the next session.